So, welcome everyone. Thanks to Professor Richard. This is going to be my first video on YouTube, even though I've been having the account for many years. And seriously, I didn't expect that my first video is going to be an assignment from physics. So once again, thank you so much, Professor, for giving me this opportunity. And my dear friends who will be watching this video. So today we are going to explore the path integral formulation of quantum mechanics proposed by Richard Feynman, a profound concept that revolutionizes our understanding of quantum physics. This approach offers a comprehensive framework for understanding how particles from one point to another, considering every possible path that it can take. So I chose this topic because it presented a significant difficulty when I was doing the assignment 8, when Professor gave us the assignment from Shankar chapter 8 on evaluating the propagator for a simple harmonic oscillator using the path integral formulation method. This problem pushed me to explore beyond the comfort of familiar equations that we have been using so far and dive into a realm where every possible path a particle might take contributes to its final behavior. It was both daunting and enlightening at the same time, enhancing my appreciation for the breadth and depth of quantum mechanics. So the real challenge began in reconciling this with the deterministic nature of classical mechanics. I wish it had been explained more early on. The quantum mechanics fundamentally challenges our classical intuitions. So not just mathematically, but philosophically, I would say. Yeah, so the cornerstone of the path integral formulation is the expression for the propagator, which in quantum mechanics describes the amplitude for a particle's transition from one point to another over time. So let's start with the general form of the equation that we use in classical mechanics. Visible. So this is the propagator that we use in the classical mechanics, but unlike classical mechanics, where only the path of least action or the least action principle is considered, quantum mechanics considers all paths. Let's say I hope this is visible. So this is the propagator that we use for classical mechanics, and this is the propagator that we use for quantum mechanics, where here the propagator shows or represents the quantum amplitude for moving from point x naught at time t naught to point x at time t. The integral sums over all the path that it would take, and dx denotes the measure over all the space of all paths, and s of x of t is the action for a particular path. So to understand the significance of the action yes in the path integral, consider its role in weightening each path. So the action for a path in the context of classical mechanics would usually dictate the least action path, but in quantum mechanics every path contributes. The action in quantum mechanics is expressed as so this is the action yes, where the x is the velocity of the path and the v of x is the potential energy. This formulation allows for the inclusion of all potential variations of a particular particles might experience along its path. So the breakthrough came when I visualized this path integral formulation through the double-slit experiment, where particles exhibit interferences that only makes sense if you consider all the path that the particles might take. This was when I truly appreciated the depth and beauty of the path integral formulation, seeing it as a natural extension of the wave-particle duality of quantum objects. So applying this to the double-slit experiment, it's a pivotal demonstration of quantum mechanics, I would say. So traditionally analyzed using wave mechanics, the path integral formulation provides a richer insight into this. So everyone knows the double-slit experiment. So So as you can see, this is the double-slit experiment. I don't need to explain more, but still this is the coherent source, and the waves are going through the double-slit, and this is the fringes that we are seeing because of the interference pattern. More fringes appear if you increase the distance between the two slits, and if you decrease the distance between the two slits, then the number of fringes that appear here also decreases. So in this experiment, particles pass through two slits and then interference on a screen Traditionally, this is explained by wave interference, but using the path integral approach, we consider that the particles do not follow a single path, but rather take every possible path from the source through the slits to any point on the screen. So, which can be explained using this pattern can be explained using the path integral formulation, and let's see. It can be explained using the path integral formulation, where each path contributes to the final behavior of the pattern on the screen. So the exponent E of ix x of t over the reduced Planck's constant, which we almost use in all the formulations of quantum mechanics, the path is contributed by this exponent, where different paths interfere due to phase differences, creating the interference pattern observed on the screen. I would like to quote a quote from Richard Feynman, where he said that all of quantum mechanics can be gleaned from carefully thinking through this implications of this single experiment. So that's how important the double slit experiment is, which really fascinated me even when thinking about this right now. And understanding the path integral in this context underscores the non-intuitive nature of quantum mechanics. It challenges the classical deterministic trajectory concept and replaces it with the possibilities that sum over an infinite path. So this has profound implications not just for foundational foundational physics, but also for practical applications in quantum mechanics and quantum technology. So to conclude, the path integral formulation isn't just a mathematical concept, but a fundamental perspective of quantum mechanics and quantum world. It allows us to visualize and compute phenomena that or otherwise cannot be explained through classical approach. So embodying the true quantum nature of particles. And thank you everyone for your attention, and I hope this presentation has deepened your understanding of path integral formulation and inspired you to explore further the fascinating phenomena it can offer. And Professor Richard Jones, thank you once again for giving me this opportunity. Thank you.